Welcome to this explainer. Today, we're going to completely shatter this illusion that there's such a thing as a perfect database. Look, if you're out there searching for a magical, one-size-fits-all solution for your application, I'm here to tell you right now, it just doesn't exist. Instead, we're going to unpack the foundational trade-offs in data systems architecture, straight from the brilliant first chapter of Designing Data-Intensive Applications.
There's this fantastic quote by Thomas Sowell that really hits the nail on the head here. He says, "There are no solutions, there are only trade-offs. But you try to get the best trade-off you can get, and that's all you can hope for." And honestly, that is the core philosophy of engineering. It's about mastering those exact trade-offs, not hunting for silver bullets. Because a system that works flawlessly for one app, it could literally be an absolute disaster for another. It is all about the context.
So here is our roadmap for today. We're going to navigate 4 major architectural forks in the road: operational versus analytical systems, cloud versus self-hosted environments, single node versus distributed architectures, and finally, data systems and society.
All right, let's jump right into part 1, operational versus analytical systems. Basically, what is the data actually doing? This distinction is incredibly important. It's all about contrasting the systems that run your daily business with the systems that analyze its history. Operational systems, we call these OLTP, are built for super-fast single-record lookups. Think of a user loading their profile or, adding an item to a shopping cart. You're usually dealing with gigabytes, maybe terabytes of data. But analytical systems, or OLAP, are just entirely different beasts. They completely ignore individual records so they can aggregate massive amounts of data, like calculating total revenue across every store for a whole year. And for that, you're talking terabytes to petabytes of data. Now, because these workloads are so fundamentally different, you rarely, actually pretty much never, want them running on the same database. If you drop heavy analytical queries onto an operational database, it's going to drag the whole thing down, and your actual end users are going to have a terribly laggy experience. So how do we bridge that gap? We use ETL pipelines, extract, transform, load. It's exactly what it sounds like. You extract the data from your fast operational database, transform it into a clean, analysis-friendly format, and then load it into a completely separate, dedicated data warehouse. Moving on to part 2, cloud versus self-hosted. Where does all this stuff actually live? This whole decision really boils down to a spectrum of control versus investment. It's the classic build versus buy. On one end of the spectrum, you have maximum control, but it requires the absolute highest investment. You're writing bespoke software and running it on your own hardware in-house. On the complete opposite end, you have maximum outsourcing. You're using cloud services or SaaS, your operations investment drops to almost zero, but you hand over practically all your control to a vendor. And that brings up a very real, pragmatic risk: vendor lock-in. If your cloud provider goes out of business, changes an API, or just arbitrarily jacks up their prices, well, you are entirely at their mercy. But the cloud isn't just about renting someone else's computer anymore. Modern cloud-native systems have totally changed the game. In a traditional architecture, storage and compute are tightly coupled on one machine. Your CPU and your hard drive are basically locked in a box together. But cloud-native architectures completely break that apart. They disaggregate storage from computation. So you could have all your files sitting in an object store, like Amazon S3, while completely separate compute nodes process that data over the network. It's huge because it means you can scale your processing power completely independently of your storage capacity.
Okay, part 3, single node versus distributed. Essentially, how big does this system need to be?
So, in the modern tech world, there's this overwhelming assumption that distributed is always better. But welcome to the terrifying physical reality of networks. When you split a system across multiple machines, things get unbelievably messy. Networks are just fundamentally unreliable. You have to deal with partial failures, where half your system crashes and the other half is just blissfully unaware. You face these brutal timeout delays where you ask a server a question and just get total silence. Did the server die? Did the network die? Is it just slow? Who knows? And debugging, it's an absolute nightmare tracking a single request across a dozen microservices. Quite frankly, if you can fit your workload on a single machine, and machines can hold massive amounts of terabytes these days, you should strongly consider just keeping it simple.
But look, if your scale absolutely demands it, and you have to distribute, you face yet another trade-off. Historically, people used shared disk architectures. This is where multiple compute machines share a giant disk array over a super-fast network. It's easier to manage for sure, but the contention, machines fighting over that shared disk, really limits your scale. Today, the much more popular alternative is shared nothing. Every node gets its own disk and its own CPU. It scales horizontally beautifully, almost infinitely. But the catch? It forces you to implement explicit sharding.
You have to manually slice up your data across those machines, which introduces incredible complexity right into your application logic.
Which brings us to our final section, Part 4, Data Systems in Society. I like to call this the final boss.
We've been talking a lot about cold logic and servers, but now we need to shift our focus to empathy, ethics, and human constraints, because our systems do not exist in a vacuum. Just think about this fascinating clash between technical architecture and societal law. How do you delete immutable data? As engineers, we love building systems using append-only data logs. They are incredibly robust, highly fault-tolerant, and designed to never lose a single byte of information. But then you have modern legal frameworks like the GDPR, which gives individuals the right to be forgotten. They literally have the legal right to demand their personal data be erased. So how on earth do you delete someone's history from a file that was explicitly engineered to never, ever be modified? It is a massive technical hurdle.
And that leads right into the broader philosophical tension happening in data right now. On one side, we have the big data philosophy. That mindset says you should maximize speculative data collection, hoard absolutely everything, just in case it gives you some cool, unforeseen insight a few years down the road. But on the exact opposite side, we have the legal and ethical principle of data minimization. This rule dictates that you collect only explicit data for a very specific purpose, and you get rid of it as soon as possible. These two concepts, they are just completely fundamentally at odds with one another.
Which leaves us with this final, lingering question to really chew on. Are we building a world that treats people with humanity and respect? As you go out there and architect your own data systems, making these hard choices between operational and analytical, cloud and self-hosted, distributed and single node, remember that those technical engineering compromises have profound real-world impacts. The data in those systems isn't just numbers. It represents real people. Thank you so much for joining me on this explainer. I really hope it leaves you looking at your own databases in a completely new light.